Why does an apple fall from a tree? It seems like such a simple question, a mundane observation from a lazy summer afternoon. But contained within that one simple act is one of the deepest and most persistent mysteries of the cosmos. Why down? Why not up, or sideways? What is this invisible tether that binds us, the air we breathe, and the oceans we sail upon to the surface of our world? For millennia, our ancestors looked up at the moon and the stars, wondering what kept them aloft while everything on Earth seemed so determined to fall. It's a question that tugs not just on objects but on the very fabric of human curiosity. A universal experience that connects every single one of us to the grand cosmic drama. This invisible pull is relentless, patient, and profoundly powerful. It is the silent force that dictates the arc of a thrown stone and the orbit of a distant planet. It holds entire galaxies together, preventing them from flying apart into the cold, empty void of intergalactic space. We feel its effects every moment of our lives, from the first time we stumble as a toddler to the effort it takes to simply lift our heads from the pillow in the morning. We are creatures born in a gravitational field, shaped by it and utterly dependent on it. And yet, for most of human history, its true nature remained a complete and utter enigma, a divine rule or an inherent property of matter that no one could quite explain. Think about it. The same influence that governs your every step also choreographs the graceful waltz of planets around our sun. It's the grand architect of cosmic structures, the master builder of the universe. Without this persistent, ever-present force, there would be no planets to stand on, no stars to light our way, and no galaxies to populate the vast emptiness of space. The story of the universe is, in many ways, the story of gravity. It's a story of falling together, of aggregation, of creation born from an inexorable pull. And so we embark on a journey to understand this fundamental aspect of reality. It's a detective story that spans centuries, featuring some of the greatest minds in scientific history. The quest to understand gravity is nothing less than the quest to understand our place in the cosmos. To read the rule book that governs the motion of everything from a grain of sand to a supercluster of galaxies. The answer to the simple question of why things fall reveals the very architecture of the universe. So what is this mysterious force? At its most basic, gravity is a natural phenomenon by which all things with mass or energy are brought toward one another. It's not something that objects do, but rather something that objects have simply by existing. Every single particle in the universe, from the tiniest atom to the most massive star, exerts a gravitational pull on every other particle. You are pulling on the Earth, and the Earth is pulling on you. You are pulling on the distant Andromeda galaxy and it is pulling right back. This cosmic attraction is woven into the very essence of matter, an invisible network of connections that links everything to everything else across the vastness of space. This force of attraction is what we call a fundamental interaction, one of just 4 that we know of that govern all the workings of the universe. The others, the strong nuclear force, the weak nuclear force, and electromagnetism, operate at the microscopic scale, holding atoms together or governing radioactivity. But gravity is the undisputed king of the macrocosm. While it is by far the weakest of the 4 forces at small scales, the magnetic pull of a small refrigerator magnet easily overpowers the gravitational pull of the entire planet. Its reach is infinite. It never turns off, and it is always attractive, tirelessly pulling matter together over unimaginable distances and cosmic timescales. The strength of this gravitational pull depends on 2 key things: mass and distance. The more massive an object is, the stronger its gravitational grip. That's why we are stuck to the Earth, a body of immense mass, and not to a nearby pebble. It's also why the Sun, which contains over 99.8% of the mass in our solar system, is the undisputed gravitational anchor, holding all the planets in their orbits. The second factor is distance. The farther away you get from an object, the weaker its gravitational influence becomes. This is why the pull of the Sun, despite its enormous mass, doesn't just snatch the Earth out of its orbit and consume it. Distance provides a crucial buffer. This simple relationship between mass and distance is the fundamental rulebook for cosmic construction. It's this interplay that allowed the universe to evolve from a nearly uniform state into the lumpy, structured cosmos we see today. Tiny, random fluctuations in density in the early universe meant that some regions had just a little more mass than others. Gravity, ever patient, went to work on these slight imperfections. The slightly denser regions pulled in more material, becoming even denser and in turn, pulling in even more material. It was a cosmic snowball effect, a feedback loop that, over billions of years, built everything we know and love. In the beginning, just after the Big Bang, the universe was an almost perfectly smooth, incredibly hot and dense fog of particles and energy. It was a sea of hydrogen and helium gas, expanding rapidly in all directions. But it wasn't perfectly smooth. There were minuscule variations in density, tiny clumps of matter that were just a fraction of a percent denser than their surroundings. In this primordial soup, gravity found its first canvas. These tiny seeds of structure became the focal points for gravity's grand construction project. The slightly denser regions exerted a slightly stronger gravitational pull, beginning the slow, patient process of gathering matter from the surrounding space. Over millions of years, these clouds of gas, under the relentless crush of their own gravity, grew larger and denser. As the particles within them were pulled closer together, they began to collide more frequently, causing the temperature and pressure at the center of the cloud to skyrocket. Eventually, the core of the cloud became so hot and dense that a new process ignited: nuclear fusion. In this cosmic furnace, hydrogen atoms were forced together to create helium, releasing a tremendous amount of energy in the process. A star was born. The outward push of this new energy battled against the inward pull of gravity, establishing a delicate equilibrium that would last for millions or even billions of years. The first stars lit up the cosmic darkness, but gravity wasn't done. These first stars were often born in clusters, great stellar nurseries where thousands or millions of stars ignited in close proximity. The collective gravity of these stars held them together, forming the first small galaxies. These were not the grand spirals we see today, but smaller, irregular collections of stars and gas. Yet the same principle applied on a larger scale. These proto-galaxies pulled on each other, their gravitational influence reaching across millions of light-years. They began to drift toward one another, drawn together by their mutual attraction in a slow, cosmic dance that unfolded over eons. This process of merging and acquisition is how the grand structures of the universe were built. Smaller galaxies collided and merged, their stars and gas clouds mixing to form larger and larger galaxies. Our own Milky Way is a product of this history, having consumed countless smaller galaxies over its 13 billion-year lifetime. On an even grander scale, galaxies themselves were pulled together into massive clusters, and these clusters were strung out along vast filaments of matter, separated by immense voids of near emptiness. This cosmic web, the largest structure in the universe, is a breathtaking testament to gravity's power as the ultimate sculptor, patiently shaping the cosmos from primordial chaos into magnificent order. For centuries, the heavens and the earth were seen as two separate realms governed by different rules. The celestial bodies, the sun, moon, and planets, moved in perfect, predictable circles, while objects on earth fell in straight lines. This all changed in the 17th century with one of the greatest leaps of imagination in human history, courtesy of Isaac Newton. The story goes that he was sitting in his garden when he saw an apple fall from a tree. At the same time, he could see the moon in the sky. In a moment of profound insight, Newton wondered if the same force that pulled the apple to the ground was also the force that held the moon in its orbit around the Earth. This was a revolutionary idea. Newton proposed that the moon is, in fact, constantly falling toward the Earth just like the apple. The reason it doesn't crash into us is that it's also moving sideways at a very high speed. Imagine throwing a stone. The harder you throw it, the farther it goes before gravity pulls it to the ground. If you could throw it fast enough, its forward motion would perfectly match the rate at which the Earth's surface curves away from it. The stone would continuously fall toward the Earth, but it would never get any closer. It would be in orbit. The moon, in Newton's view, was just a very large cannonball forever falling but always missing. Newton didn't just stop at this brilliant insight, he quantified it. He formulated a precise mathematical law to describe this force, which he called the law of universal gravitation. He stated that the force of gravity between any two objects in the universe is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This means that if you double the mass of one object, the gravitational force doubles. But if you double the distance between them, the force becomes 4 times weaker. This inverse square law was the key that unlocked the motions of the heavens. With this single, elegant equation, Newton could explain not only why apples fall, but also the orbits of the planets, the paths of comets, and the ebb and flow of the tides. It was a moment of true unification, demonstrating that the laws of physics that operate in our everyday world are the same laws that govern the cosmos. The universe was no longer a mysterious, divine realm. It was a rational, predictable system, a grand clockwork mechanism that could be understood through mathematics and observation. Newton's law was a triumph of the human intellect, and it reigned supreme as our best description of gravity for over 200 years. For more than 2 centuries, Newton's law of gravity worked beautifully. It predicted the motions of planets with stunning accuracy and even led to the discovery of Neptune based on irregularities in the orbit of Uranus. But by the early 20th century, a few tiny cracks began to appear in this majestic edifice. One nagging problem was the orbit of Mercury. The closest planet to the Sun, Mercury's orbit wasn't behaving exactly as Newton's law predicted. It was a tiny discrepancy, but it hinted that something was missing from the story. A young patent clerk named Albert Einstein was about to provide a completely new, and much stranger, explanation. Einstein's journey began with a thought experiment. What would it be like to fall freely in an elevator whose cable had snapped? Inside the elevator, you and any objects with you would be weightless. If you dropped a ball, it would just float there beside you. From your perspective inside the falling elevator, gravity would seem to have vanished. This led Einstein to what he called his happiest thought, the idea that gravity as a force and acceleration are indistinguishable. He realized that gravity wasn't a force pulling things across space, but rather something much more profound. He proposed that gravity is the result of mass and energy warping the very fabric of reality. Einstein imagined that space and time are not separate, static backdrops to the events of the universe, but are fused together into a single, 4-dimensional continuum called spacetime. He then proposed that massive objects like stars and planets create curves or warps in this spacetime fabric, much like a heavy bowling ball creates a dip in a stretched-out trampoline. Smaller objects, like planets or comets, aren't being pulled by a force from the sun. Instead, they are simply following the straightest possible path through the curved spacetime created by the sun's immense mass. The Earth orbits the sun for the same reason a marble rolls around the inside of a cone. It's following the curve of the surface it's on. This new picture of gravity, which he called the general theory of relativity, was a radical departure from Newton. Gravity was no longer a mysterious force acting at a distance, it was a consequence of the geometry of the universe itself. It explained the strange orbit of Mercury perfectly. The planet was so close to the sun that it was rolling along a very steeply curved part of spacetime. Einstein's theory also made other startling predictions, such as that light itself should be bent by gravity. This was confirmed during a solar eclipse in 1919, when astronomers observed that starlight passing near the sun was deflected by exactly the amount Einstein had predicted. Newton's clockwork universe was replaced by Einstein's flexible, dynamic spacetime. If gravity is the curvature of spacetime caused by mass, what happens if you put an enormous amount of mass in a very small amount of space? Einstein's theory of general relativity provided a truly mind-bending answer. You can warp spacetime so severely that it essentially tears a hole in the fabric of reality. This is a black hole, the most extreme and mysterious manifestation of gravity in the entire universe. It represents a point where gravity has become so overwhelmingly powerful that nothing, not even light, the fastest thing in the cosmos, can escape its grasp. It is the ultimate cosmic prison, a place where the known laws of physics break down. A black hole is formed when a very massive star, much larger than our sun, runs out of nuclear fuel at the end of its life. The outward pressure from fusion that had been supporting the star against its own weight suddenly ceases. With nothing to hold it up, the star's core collapses catastrophically under its own immense gravity. It implodes in a fraction of a second, crushing matter down to an infinitely small point of infinite density called a singularity. Surrounding this singularity is a boundary known as the event horizon. This isn't a physical surface, but rather the point of no return. Once you cross the event horizon, your future contains only one destination, the singularity at the center. The effects of a black hole on its surroundings are profound. As matter like gas and dust from a nearby star gets drawn in, it forms a swirling, superheated structure called an accretion disk. The friction and intense gravitational forces in this disk heat the material to millions of degrees, causing it to glow brightly with X-rays and other forms of high-energy radiation. This is how we can see black holes, even though they emit no light themselves. We detect the brilliant death spiral of matter being consumed by them. Furthermore, the intense curvature of space-time around a black hole acts like a powerful lens, bending and distorting the light from stars and galaxies behind it, a phenomenon known as gravitational lensing. Black holes represent the ultimate victory of gravity over all other forces. They are places where time itself is warped, slowing to a near standstill at the event horizon relative to a distant observer. They challenge our understanding of space, time, and the very nature of matter. They are cosmic laboratories for testing the limits of Einstein's theory, and they hint that our picture of gravity is still incomplete. What happens to the information that falls into a black hole? What lies within the singularity? These are some of the deepest questions in all of science, and they place black holes at the very frontier of our cosmic exploration, beckoning us toward a deeper, more complete theory of reality. While gravity sculpts galaxies and forges black holes in the depths of space, its influence is just as profound and intimate here on our home planet. We live our entire lives immersed in its constant, unwavering pull. It's the reason we have weight, the force the Earth's mass exerts on the mass of our bodies. If you were to stand on the moon, which has much less mass than the Earth, you would weigh only about 1/6 of what you do here, even though your own mass hasn't changed. Gravity is the silent partner in every action we take, from the simple act of standing up to the complex ballet of launching a rocket into space, which is really just a powerful, controlled struggle against the planet's relentless pull. Gravity's most dramatic terrestrial display is perhaps its command over the Earth's oceans. The rhythmic rise and fall of the tides are a direct consequence of a gravitational dance between the Earth, the Moon, and the Sun. The Moon's gravity pulls on the Earth, and it pulls more strongly on the side of the Earth that is closest to it. This causes the water on that side to bulge out toward the Moon, but it also pulls the solid Earth away from the water on the far side, creating another bulge there. As the Earth rotates beneath these two bulges, coastal areas experience 2 high tides and 2 low tides each day. The influence of gravity extends to every drop of water on the planet. It's the force that pulls rain from the clouds to the ground, feeding the rivers and replenishing the oceans. It dictates the flow of those rivers, carving canyons and shaping landscapes over geological timescales. The very existence of our atmosphere, the blanket of air that we need to breathe and that protects us from harmful solar radiation, is a gift from gravity. The Earth's mass is large enough to hold on to this precious layer of gas, preventing it from simply drifting off into space. Smaller worlds like Mars have a much weaker gravitational grip, which is one reason why their atmospheres are so thin and tenuous. Even the very structure of our planet is a product of gravity. In its early molten state, gravity pulled the heaviest materials like iron and nickel down to the center, forming the dense core. Lighter, rocky materials floated to the top, forming the mantle and the crust on which we live. This process, known as planetary differentiation, is entirely driven by gravity. It created the layered structure that generates Earth's protective magnetic field and drives the plate tectonics that recycle our planet's surface. From the air we breathe to the ground beneath our feet, every aspect of our world has been shaped and is continuously governed by this silent, persistent, and fundamental force. Gravity is not just a force that shapes planets and stars, it is a fundamental environmental factor that has shaped the evolution of every living thing on Earth. From the moment life first emerged, it had to contend with this constant downward pull. Plants, for example, must fight a continuous battle against gravity to grow upwards toward the life-giving light of the sun. They have evolved strong, rigid structures like cellulose and lignin in their cell walls to provide the necessary support to stand tall. Their root systems also respond to gravity, a phenomenon called gravitropism, growing downward to anchor the plant and seek out water and nutrients deep in the soil, ensuring their stability and survival. Animals, too, are masterpieces of gravitational engineering. The evolution of skeletons, whether internal like our own or external like an insect's, is a direct response to the need to support a body's weight against gravity's pull. Our bones are incredibly strong yet lightweight, a perfect compromise for moving efficiently within a gravitational field. Our muscles have developed to provide the force needed to overcome gravity, allowing us to walk, run, and jump. Even our circulatory system is designed to pump blood uphill from our feet back to our heart, with special valves in our veins to prevent gravity from pulling it all back down. Every aspect of our physiology is finely tuned to the specific gravitational conditions of our planet. Life on Earth has become so accustomed to this force that its absence causes significant problems. When astronauts spend extended periods in the microgravity environment of space, their bodies begin to change. Without the constant stress of gravity, their bones start to lose density, becoming more brittle, a condition similar to osteoporosis. Their muscles, including the heart, begin to atrophy from lack of use. This profound connection between life and gravity raises some fascinating questions as we look to the stars. Could life evolve on a planet with much higher gravity? Such creatures would likely be shorter, stockier, and incredibly strong. What about a low-gravity world? Perhaps life there would be tall, thin, and delicate. The search for extraterrestrial life is not just a search for water and a temperate climate, it's also a search for worlds where the force of gravity falls within a range that could support the complex structures of biology. Gravity, it seems, is not just a stage for life to play out on, it is a fundamental director of the evolutionary play itself. We have two pillars of modern physics that describe the universe with breathtaking success. General relativity, Einstein's theory of gravity, is the master of the very large. It perfectly describes the behavior of planets, stars, galaxies, and the expansion of the universe itself. On the other hand, we have quantum mechanics, the theory of the very small. It governs the bizarre and wonderful world of atoms and subatomic particles with equally stunning accuracy. Both theories work flawlessly in their own domains. But there is a problem, a deep and troubling chasm in our understanding of the cosmos. These two theories are utterly incompatible with each other. The conflict arises when we try to describe situations where the very large meets the very small, that is, where immense gravity operates on a microscopic scale. The two prime examples are the singularity at the center of a black hole and the state of the universe at the moment of the Big Bang. In these extreme environments, you have a massive amount of matter and energy crushed into an infinitesimally small space. To understand what's happening, you need both general relativity and quantum mechanics. But when you try to apply their equations together, they break down, yielding nonsensical answers like infinities. This tells us that our current understanding is incomplete. We are missing a deeper theory. The quest for this missing piece of the puzzle is the search for a theory of quantum gravity. This is arguably the most profound challenge in all of physics today. The goal is to develop a single framework that can describe gravity in the language of quantum mechanics. Such a theory would explain what gravity is at its most fundamental microscopic level. Is it carried by a hypothetical particle, a graviton, just as the electromagnetic force is carried by photons? Does space-time itself dissolve into discrete, pixel-like chunks at the tiniest possible scale, the so-called Planck length? These are the questions that keep theoretical physicists up at night. Leading candidates for a theory of quantum gravity include ideas like string theory, which proposes that all fundamental particles are actually tiny, vibrating strings of energy, and loop quantum gravity, which suggests that space-time itself is built from a network of interlocking quantum loops. These theories are incredibly complex and operate at energy scales far beyond what we can test with current technology. But the search continues, driven by the conviction that the universe at its deepest level must be described by a single, elegant, and unified set of laws. Finding this theory would not only solve the mystery of black holes and the Big Bang, but would represent the ultimate unification of our knowledge, a true theory of everything.